Hi everyone, I am Dr. Srinivasa Kumar. Welcome to my lectures on vector differentiation. This is part 6 of my series of lectures on this topic. In this present lecture, we concentrate on the following: conservative vector fields, potential functions. At last, we solve a few problems. What are conservative vector fields? A vector field cap F from R3 to R3 is said to be a conservative vector field if there exists a scalar field phi satisfying cap F equals grad phi. That means here a vector field is given to us, big F. Corresponding to this big F, we need to find out a scalar field phi from R3 to R satisfying the condition grad phi equals cap F. This phi from R3 to R is called a potential function of the given vector field. That means a vector field F is given to us. We need to find out a scalar field phi from R3 to R such that its gradient is equal to the given vector field F. Then the given vector field is called a conservative vector field and the scalar field which we find is called a potential function. Conservative vector fields and potential functions are very important in the applications of engineering mathematics. We say that a vector field is a conservative vector field if we can find out a scalar field phi whose gradient equals the given vector field. We can't find out a scalar field phi in such a way that its gradient equals the given vector field directly. So we need a shortcut in doing problems. Here, if we take a vector field big F, if it is conservative, then it is equal to the gradient of some scalar field phi. If we find out curl on both sides, curl F equals curl of grad phi. We have seen already that curl of grad phi equals 0 cap. Hence curl F equals 0 cap. This is very useful to verify that the given vector field is conservative or not. If a vector field F from R3 to R3 is a conservative vector field, then its curl equals 0 cap. If curl F is not equal to 0 cap, then the given vector field is not a conservative vector field. So in every problem, if we want to prove that a given vector field is conservative, first we find out its curl. If curl F equals 0 cap, we conclude that the given vector field F is conservative. If curl F not equal to 0 cap, we conclude that F is not a conservative vector field. So far, we have seen how to verify that the given vector field is conservative or not. We find its curl. If curl is 0 cap, then the given vector field is conservative, otherwise it's not. Now the main problem is how to find out a potential function of the given vector field. Let us see the procedure. First, let us consider a vector field f from R3 to R3. In the first step, we need to verify whether the given vector field is conservative or not. That means we verify that curl f equals 0 cap or not. In this procedure, let us suppose that curl f equals 0 cap. Then f becomes a conservative vector field. If it is conservative, we need to find out its potential function. That means we need to find out a scalar field whose gradient is the given vector field. Since f is conservative in this process, let us write down the definition. There exists a scalar field phi from R3 to R in such a way that grad phi equals the given vector field f. First, let us represent f by using its component functions. F can be written as f equals small f1 I cap plus small f2 j cap plus small f3 k cap. Grad phi equals I cap dou phi by dou x plus j cap dou phi by dou y plus k cap dou phi by dou z. Since f equals grad phi, let's equate these two vectors. So f1 I cap plus f2 j cap plus f3 k cap equals dou phi by dou x I cap plus dou phi by dou y j cap plus dou phi by dou z k cap. That implies f1 equals dou phi by dou x, f2 equals dou phi by dou y, and f3 equals dou phi by dou z. We have already written the component functions f1, f2, f3 in terms of the scalar point function phi. That means we have written f1 equals dou phi by dou x, f2 equals dou phi by dou y, and f3 equals dou phi by dou z. Here we must remember two things. The first thing is a vector field capital F is given to us. Since capital F is a given vector field, it is a known function. Because capital F is a known vector field, its component functions small f1, small f2 and small f3 are also known functions. But the scalar point function phi is an unknown function. In this problem, our target is to find out this scalar point function phi. In order to find out phi, we start with the equation f1 equals dou phi by dou x. Consider the equation f1 equals dou phi by dou x. Integrate this equation with respect to x on both sides by treating the other two variables y and z as constants. Then we obtain integral f1 dx is equal to integral dou phi by dou x dx plus some constant. This can be written as integral f1 dx equals phi of x comma y comma z plus h of y comma z. In this equation, h of y comma z represents a constant in terms of the variables y and z. It is an integrating constant. Now consider the equation integral f1 dx equals phi of x comma y comma z plus h of y comma z. Let us suppose that this equation is 1. If we find out h of y comma z in this equation 1, we are done. From this, we can find out our required scalar point function phi whose gradient is the given vector field f. To find out phi, now consider equation 1. Differentiate equation 1 partially with respect to y on both sides. Then we obtain dou by dou y integral f1 dx equals dou phi by dou y plus dou by dou y h of y comma z. In this equation, we know the value of dou phi by dou y. It is nothing but the second component function f2. Let us substitute f2 in the place of dou phi by dou y. Then this equation can be rewritten as dou by dou y integral f1 dx equals f2 plus dou by dou y h of y comma z. Now we integrate this equation with respect to y by treating z as a constant. By integrating the equation with respect to y by treating z as a constant, from that we can find out the value of h of y comma z. h of y comma z can be written in the form h of y comma z equals psi plus g of z. In this particular equation, g of z represents a constant in terms of z. Now we substitute the value of this h of y comma z in the equation 1. Then we obtain integral f1 dx equals phi of x comma y comma z plus psi plus z of z. In this present equation, we know the values on the left hand side. On the right hand side, we know psi value. We need to find out z of z. To find out z of z, we take this equation integral f1 dx equals phi of x comma y comma z plus psi plus g of z. We differentiate this particular equation with respect to z partially on both sides. From the resultant equation, we can find out the value of z dash of z. After finding z dash of z, by integrating with respect to z on both sides, we can obtain the value of z of z. This g of z value we substitute in equation 3. From that, we find out our required scalar point function phi of x comma y comma z, which is our required potential function for the given vector field. Now let us solve a few problems. In the first problem, we are given a vector field f of r cap. We need to prove that this vector field f of r cap is a conservative vector field. To show that a vector field is conservative, we have to prove that its curl is 0 cap. So here we have to show that curl of f of r cap equals 0 cap. To prove this, consider the vector r cap equals xi cap plus yj cap plus zk cap. Multiply this vector with f of r on both sides. Then we obtain f of r cap equals f of r x I cap plus f of r y j cap plus f of r z k cap. For this vector field f of r cap, the component functions are f1 equals f of r x, f2 equals f of r y, f3 equals f of r z. Now curl of f of r cap equals a 3 by 3 determinant I cap, j cap, k cap on the first row, dou by dou x, dou by dou y, dou by dou z on the second row, f1, f2, f3 on the third row. Here we have to substitute the component functions. f1 equals f of r x, f2 equals f of r y, f3 equals f of r z. Then curl of f of r cap equals I cap, j cap, k cap on the first row, dou by dou x, dou by dou y, dou by dou z on the second row, f of r x, f of r y, f of r z on the third row. To expand this determinant, we need to find out the following partial derivatives first. First we find out the partial derivative dou by dou y of f of r z. Dou by dou y of f of r z equals z times dou by dou y of f of r. That equals z times f dash of r dou r by dou y. We very well know that the value of dou r by dou y. Dou r by dou y equals y by r. If we plug in that value here, we get dou by dou y of f of r z equals z f dash of r y by r. Now we find our next partial derivative dou by dou z f of r y. Dou by dou z f of r y equals y dou by dou z f of r. That equals y f dash of r dou r by dou z, which equals y f dash of r z by r. Here we observe one fact. The two partial derivatives dou by dou y f of r z equals dou by dou z f of r y. Similarly, dou by dou x f of r z equals dou by dou z f of r x, and dou by dou x f of r y equals dou by dou y f of r x. Now the curl of f of r cap equals I cap times dou by dou y f of r z minus dou by dou z f of r y minus j cap times dou by dou x f of r z minus dou by dou z f of r x plus k cap times dou by dou x f of r y minus dou by dou y f of r x. Here, in the coefficient of I cap, those two partial derivatives are equal, so their difference is 0. Similarly, the coefficient of j cap and the coefficient of k cap are 0. Hence, curl f of r cap equals 0 I cap plus 0 j cap plus 0 k cap. That equals the 0 vector 0 cap. So, curl f of r cap equals 0 cap. If the curl of a vector field is 0 cap, then we say that the vector field is irrotational, or we can also say that it is a conservative vector field, because curl f of r cap equals 0 cap. The given vector field f of r cap is irrotational, and we can also say that it is a conservative vector field. We are done. If a vector field is conservative, we have already seen a procedure to find out a scalar potential function for the given conservative vector field. Let us solve a problem by using that process. Problem 2. In this problem, a vector field is given to us. We need to prove that it is conservative. Next, we have to find out a scalar field whose gradient is equal to this given vector field. That means this problem has two parts. In part 1, we have to show that the given vector field is conservative. In the second part, we have to find out a potential function for the given vector field. Let us see the first part. The given vector field is f is equal to 2xyz square I cap plus x square z square plus z cos yz j cap plus 2x square yz plus y cos yz k cap. We have to show that this vector field is conservative. To show that this is conservative, we have to prove that its curl is 0 cap. Let us do that first. Consider the given vector field f is equal to 2xyz square I cap plus x square z square plus z cos yz j cap plus 2x square yz plus y cos yz k cap. Let us write down the component functions of the given vector field. The component functions are f1 is equal to 2xyz square, f2 is equal to x square z square plus z cos yz, f3 equals 2x square yz plus y cos yz. Let us show that this given vector field is conservative. For that purpose, let us find out its curl. So, curl f is equal to a 3 by 3 determinant I cap, j cap, k cap on the first row, dou by dou x, dou by dou y, dou by dou z on the second row, f1, f2, f3 on the third row. We know that instead of f1, f2, f3, we have to substitute their values. Then the determinant becomes I cap, j cap, k cap, dou by dou x, dou by dou y, dou by dou z, 2x yz square, x square z square plus z cos yz, 2x square yz plus y cos yz. If we expand this determinant with respect to the first row, we get 0 cap. Verify this yourself. So curl F equals 0 cap. So the given vector field capital F is an irrotational vector field. We can also say that the given vector field is a conservative vector field. This completes the part 1 of our problem. After proving the given function is conservative, we have to find out its potential function. Because the given vector field capital F is conservative, according to the definition, there exists a scalar point function phi from R3 to R in such a way that grad phi equals capital F. Now we have to find out this phi. Now we have to equate the vectors capital F and grad phi. If we equate capital F and grad phi, I cap F1 plus j cap F2 plus k cap F3 equals I cap dou phi by dou x plus j cap dou phi by dou y plus k cap dou phi by dou z. Then we get F1 equals dou phi by dou x, F2 equals dou phi by dou y and F3 equals dou phi by dou z. Thus, we have written the values of the component functions f1 and f2, f3 by using the scalar point function phi. Now, to find out the scalar point function phi, we consider the first equation f1 equals dou phi by dou x. In this equation, we have to substitute the value of the first component function f1 on the left hand side. Then this equation becomes 2x yz square equals dou phi by dou x. Now integrate this equation with respect to x on both sides by treating the other two variables y and z as constants. If we do so, we get x square yz square equals phi of x comma y comma z plus h of y comma z. In this equation, h of y comma z is a constant in terms of y and z. Let us suppose that this equation is number 1. Here we have to find out h of y comma z value. To find out h of y comma z, consider this equation 1. X square yz square equals phi of x comma y comma z plus h of y comma z. Differentiate this equation partially with respect to y on both sides. Then the left hand side of this equation becomes x square z square. The right hand side becomes dou phi by dou y plus dou h by dou y. All together, equation 1 becomes x square z square equals dou phi by dou y plus dou y h of y comma z We know the value of dou phi by dou I, that is nothing but the second component function f2. Let us substitute f2 in the place of dou phi by dou I. Then we obtain x square z square equals f2 plus dou by dou I h of y comma z. Now we substitute the value of f2 in this equation. Then we get x square z square equals x square z square plus z cos yz plus dou by dou I h of y comma z, because the value of f2 is x square z square plus z cos yz. We cancel x square z square on both sides in that equation. Then we get 0 equals z cos yz plus dou by dou I of h of y comma z. From this equation, we find the value of dou by dou I h of y comma z. We get dou by dou I h of y comma z equals minus z cos yz. We integrate this equation with respect to y on both sides by treating z as a constant. Then we get integral dou by dou I h of y comma z is equal to integral minus z cos yz plus some constant. Then we get h of y comma z is equal to minus z sin yz whole divided by z plus some constant. This gives us h of y comma z equals minus sin yz plus g of z. In this equation, g of z is an integrating constant in terms of z. Now we substitute this value of h of y comma z in the equation number 1. If we substitute h of y comma z equals minus sin yz plus g of z in the first equation, we obtain x square y z square equals phi of x comma y comma z minus sin yz plus g of z. Now our aim is to find out the value of g of z. To find out g of z, we differentiate this equation with respect to z on both sides. Consider x square y z square equals phi of x comma y comma z minus sin yz plus g of z. If we differentiate partially with respect to z on both sides, this equation becomes 2x square yz is equal to dou phi by dou z minus y cos yz plus g dash z. Now we substitute dou phi by dou z equals f3. Then the equation becomes 2x square yz equals f3 minus y cos yz plus g dash of z. In the place of f3, we have to substitute the value of f3. Then this equation becomes 2x square yz equals 2x square yz plus y cos yz minus y cos yz plus g dash z. Now everything cancels out and we get g dash z is equal to 0. From this, g of z is equal to c, where c is a constant. We substitute g of z is equal to c in equation 3. Then we get x square y z square is equal to phi of x comma y comma z minus sin of yz plus c. From this equation, we find phi of x comma y comma z implies phi of x comma y comma z equals x square yz square plus sin yz minus c. Of course, we can take plus c as a constant also. This is the required potential function for the given vector field F. We are done. The present lecture mainly focuses on vector fields which are conservative, and we found potential functions for the conservative vector fields. For further queries, you can contact me through mail. Thanks for listening.